Watch how this filament ignites, a sudden burst of energy, light, and heat. The physical universe appears as a sequence of complex, overlapping events. But to understand these phenomena, we need a way to move beyond simple observation. Without a standardized system to quantify what we see, scientific communication becomes impossible. Observations remain subjective, and the data remains unstructured. This is why we define a physical quantity. It is the specific property of a phenomenon, body, or substance that can be quantified through measurement. By identifying these quantities, we transform chaotic natural events into data that can be analyzed and compared. Every physical quantity requires two distinct parts to be useful: a magnitude and a unit. The magnitude is expressed by a real number. It provides the scale or the amount of the property being measured. The unit provides the agreed-upon standard of reference. Whether it is meters, kilograms, or seconds, the unit gives the number its physical meaning. All measurable properties are classified into two categories: fundamental quantities and derived quantities. This combination of a number and a standard unit creates the baseline required to compare every object in the known environment. Fundamental physical quantities are the starting points of measurement. These are properties that have their own specific values and cannot be explained by or broken down into any other quantities. There are exactly 7 fundamental quantities that form the basis of all physical measurement. The first 3 cover the mechanics of space and time: length, measured in meters; mass, measured in kilograms; and time, measured in seconds. Then we have temperature, measured in Kelvin, and the amount of a substance, measured in moles. The list is completed by electric current, measured in amperes, and luminous intensity, measured in candelas. These 7 irreducible properties are the foundational components used to construct every other concept in physics. Derived physical quantities are measurements created by combining those 7 fundamentals through mathematical operations. Velocity is a clear example. It is derived by dividing a fundamental length by a fundamental time, resulting in meters per second. If we divide that velocity by time again, we get acceleration, expressed as meters per second squared. Multiplying mass by acceleration gives us force, which we measure in newtons. Some are simpler. Volume is derived by multiplying a fundamental length by itself 3 times, giving us cubic meters. And when we multiply force by length, we define work, measured in joules. Not every quantity follows this exact pattern. A few specific properties, such as plane angles, solid angles, and elastic modulus, are unitless. By mathematically arranging just 7 fundamental elements, we can quantify complex interactions ranging from simple motion to the expenditure of energy. In practice, physical quantities are obtained in one of 2 ways. They are either measured directly with an instrument or calculated using a mathematical formula. While instruments are typically used to capture fundamental quantities, mathematics allows us to generate the derived quantities that describe the broader world. To summarize, first, a physical quantity must possess both a magnitude and a unit. Second, the system relies on the specific independent values of the 7 fundamental quantities. And third, all other measurements are derived combinations of those foundational 7. From laboratory experiments to astronomical observations, this structured hierarchy of measurement provides a consistent framework for describing the physical world.